Right. Good evening, everyone. Welcome once again to another contract in blockchain unions web tribute camp. Uh, for today's class, we'll be having one of our tutors, Idogwu Chinonso, walk us through upgradable smart contracts. Basically, you're going to be learning how to build smart contracts that you can upgrade. Right. I know right before I've probably told you that smart contracts are not upgradable, are supposed to be constant and stuff, right? But we're going to be introducing you to how you can actually build upgradable logics, right? And we'll be having Chinon to take us through the class. So if you know someone who's supposed to be here, who not here yet, please send the person a DM, and we are going to be getting started now. Yeah, Chin, so please, if you can hear me, you could get started.
Okay, yeah, that's fine. That's fine. Okay, so good evening, everyone. Um, my name is Idogwu Chinonso. I know you guys already know that. I took you guys a while back on oracles. So today we'll be continuing with upgradable smart contracts, and the class is going to be divided into two sections. The first section is going to be more of like a theoretical session where I just put you guys through what upgradability in smart contract means, what the concept actually means. We're going to be touching the different types of implementations for upgradable smart contracts. And finally, the second session will be doing a live coding session where we'll be designing a proxy contract. So we'll design a contract, I'll um, deploy it, then we will interact with it. Then we're going to upgrade that contract to a new implementation. Then you guys will also interact with it and see the difference. So you're able to confirm for yourself that the logic behind the contract actually changed and how it was actually able to change. So the main goal is that by the end of this session, you guys should have a strong understanding of upgrading smart contracts, how to upgrade smart contracts, and the entire concept which behind upgradability in smart contracts. So without wasting much time, I'll go straight up to start sharing my screen and putting you guys through the first session of the class. Yeah, also, so from the knowledge I have so far, I think you guys, your last class was on Foundry. So we're building on that same knowledge today. Our project today is going to be bootstrapped with Foundry. I do hope you guys actually understood or you've had time to go through the Foundry class and at least play around with Foundry. So I'd like to hear from you guys. Like, are you guys able to try out anything with Foundry? Hope you guys are cool with you continuing the class today with Foundry. Somtochiku, Nemeka, Alex.
Yeah, I'm okay with it.
Okay.
Well, I wasn't present the last class, so we can like break it down a bit.
Okay. We'll see what we can do about that. Probably try to take things slow. For today's class, we are actually touching on Foundry. So I won't be able to really go down and explain everything to you unless it's going to affect the time for today's class. So I'll just advise that you pick what you can pick from today's class. Focus majorly on what I'll be teaching today on readability in smart contracts. Then there's a recording available for the Foundry class. So after today, you can go back and go through the recordings for the Foundry class. But it's all good actually. Okay. So I hope you guys can see my screen.
Yeah, I can see your screen.
Okay, that's good. So we'll be starting today, just like I said, with upgradable smart contracts. So I'm sure we all know what smart contracts are. Smart contracts are basically self-executing agreements or programs that are written and are hosted on the blockchain. So they automatically execute action based on predefined conditions, and they basically eliminate the need for intermediaries. They reduce costs, reduce trust, and also build on blockchain technology to ensure immutability and security. So basically, you know that smart contracts are actually set of programs that are written on the blockchain that everybody can actually see. They are transparent. Everybody can go to this code, audit this code, and trust this code. So with the help of smart contracts, you are reducing the need of you trusting a centralized third party. So all you just need to do is you verify the code, you see the code, you trust the code. Before today, I know during the course of the last class or the previous classes, we've talked about smart contracts, are immutable, this, blah, blah, blah. But it's just like going through from primary school to secondary school. They'll tell you that 1 minus 2, maybe in primary school, they tell you that it's not possible. You can't remove, you can't subtract 1 from 2. But when you get to secondary school, you start getting into concepts like minus 1 and stuff like that. So it's not exactly the same, but it's a similar concept to upgradability in smart contracts. In as much as we've been hammering that smart contracts are actually immutable, this and that. But to an extent, smart contracts, not even to an extent, smart contracts are actually immutable. But our smart contracts can actually, through some certain mechanisms, be upgraded. But it doesn't remove from the fact that, or it doesn't derail the fact that smart contracts are actually immutable. So we understand what smart contracts are at this point. Then we begin to the need for upgradability. So traditionally, before today, smart contracts lack the ability to be modified, and this this particular problem hinders the um, ability of smart contracts to actually upgrade or to meet up with the current standards. So every day there are new updates to the blockchain systems, there are new updates to the computer world in general. A code you write today that might actually be safe, tomorrow might be termed as a bug or a vulnerability. So, and if it's unable or if it's impossible for our contracts to actually upgrade to meet up with this standard, it's going to actually be an issue. Because imagine if you write a contract that is holding a lot of funds, a poor contract as you write basically as developers now, you write a contract to save your funds and you are using a particular library and tomorrow you hear that okay, there's a vulnerability in this library and stuff like that. So if it's impossible for our smart contract to actually be upgraded, then it's going to actually mean that you have to basically empty that particular contract if it's possible, then abandon it because that contract at that point lacks the ability or lacks the functionality for it to be upgraded in order to um, cancel out in order to remove that particular vulnerability. So this is just one example of the need for upgradability in smart contracts. So there are multiple reasons why we want to upgrade our smart contracts as developers. One, there might be new ideas, there might be new ways or new methods to implement things that are more gas efficient. So you might want to update that. There might be new ways to carry out execution of functions that are more user inclined, probably more user friendly. For example, okay, we know that for Uniswap, if you're carrying out any swap or stuff like that, traditionally you have to first of all grant approval to like the swapping contract before you even execute the transaction. But tomorrow now there might be a new update to Solidity that's going to allow you to actually execute multiple transactions or batch these transactions together and execute them in one go. So there might be a need or there might be an urge for you as a developer to want to actually upgrade your traditional smart contract to the latest standard, unless you're going to be outdated in the system. So these are just some of the needs. There may also be a vulnerability in your smart contracts that you've noticed. And at that point, you just need to upgrade it to a new implementation that's going to cancel out that vulnerability. So all these things are reasons or needs that arise that actually led to developers thinking of ways to actually upgrade or implement observability in smart contracts. So basically, in terms of the needs for observability and also the benefit of observability, they go hand in hand. Most of the problems we experience or most of the concepts that led to a need for our smart contracts to be upgradable are actually the benefits we enjoy when those contracts are actually upgradable. So if you implement a contract that is upgradable, if there's a bug, you can basically fix that easily. All you just need to do is write a better implementation or a code that doesn't contain that particular bug or that fixes that bug, then all you just need to do is upgrade your previous implementation to the latest standard, and that's it. If there's any new implementation you want to add to your contract, all you just need to do is write a new contract that follows the new standard implementation, then upgrade the previous contract. That way, you maintain your user, you maintain your data, and users basically don't some in most of these upgrades, users don't necessarily need to know that they've been an upgrade. They just continue interacting with the same address. Imagine a user, okay, for example, you know pancake swap address. I know that okay, this pancake swap address, this Uniswap address, this 1 inch address, and there's a bug in it today. Tomorrow, Uniswap just released a notification that okay, we upgraded our contract due to this vulnerability. And you as a user, you basically you use Uniswap yesterday, you're using it today, and they're telling you that they've run an upgrade and they've changed certain things in it. So it gives users this sense that okay, my funds are secured, also covered. If there are any issues, there will be an upgrade, and I don't even need to bother about these things. And my funds are safe, everything is still running the way they're supposed to run. So these are just some benefits some need, and also some benefits we enjoy when we implement upgradable smart contracts. Then when it comes to the implementation approach, there are basically multiple approach or multiple ways to implement upgradable smart contracts. Some of these methods involves the use of proxy contracts, where logic are spread in one contract, while the actual storage, by storage, I mean, okay, for example, if you're writing an ERC20 contract, the implementation for the transfer, the implementation for the mint, the implementation for transfer form are in one contract, the functions are in one contract. Then the actual storage that are holding the balance of all the users, that are holding the approvers that all the users are in a different contract. So that way, if there's any issue in the logic, most times when it comes to bugs and all this, the problems are always in the logic. And that means in cases like this, all you just need to do is to upgrade the second contract holding the logic, holding the functions, while you still maintain the storage, which is where all the balance of the users are, all the approvers they planted and stuff like that. So with that, you can always change the functions. You can always change the implementations of the function while still maintaining the storage, while still maintaining the balance of your users. So that's just like like an overhead view of what policy contracts are and how they work. So the other approaches like utilizing libraries or utilizing delegate call in order to achieve observability in smart contracts. So I just mentioned delegate call, and I know some of you might not. Do you guys know what delegate call is? So some to Henry, Nemeka, does any of you know what delegate call is?
I
Not
feel
yet,
like
sir.
You
I feel
said?
like it's calling something. I feel like it's calling something on behalf of another thing. That's like a maybe one contract is calling another contract on behalf of a user or something like that.
Okay. Yeah, that's to an extent that's correct. So it's basically just like okay, from the word delegate, you're delegating someone to attend an event for you or something like that. So imagine, for example, if the governor of Enugu State, for example, is supposed to actually visit UNN for an event, then that governor or the governor of Enugu State at the moment is not able to attend the event. So what he does is that he sends a representative, he sends a delegate to attend the event on his behalf. If that delegate actually comes to the event and promise the organizers of that event 1 million naira, let's say he's donating 1 million naira to the organizers to handle something or stuff like that. You know, in this particular sense now, it's not just the user or the representative that actually made that promise. In this case now, it's the governor of Enugu State himself that made that promise because that user at that moment is a representative of the governor of Enugu State. So that's more of like a basic idea of how delegate call works. So with delegate call, we have two contracts, contract A and contract B. So what happens is that contract A makes a call to contract B to run certain executions. Then after running those executions, the outcome of the execution, the state changes of the execution are not actually stored in contract B. Instead, they are stored in contract A. Just for example, I'm a contract. Then let's say Henry is also a contract. The user is interacting with me in order to run 1 plus 1 on Henry's contract. So user interacts with me and make a call to Henry's contract to run the 1 plus 1. Henry's contract has the logic or has the function to run that 1 plus 1. So I make a call to Henry's contract. Henry's contract runs the 1 plus 1, gets the result. Then instead of storing that result in Henry's contract, the result instead is stored in my own contract. So okay, I think there was a kind of like distortion. So instead of the data, instead of the outcome of the execution to be stored on Henry's contract, the outcome of the execution is actually stored on my own contract, me making that call. So Henry's contract basically at this point is used just like, let's say, as a machine that just runs the execution, runs the implementation. But the state changes. Every other implementation is stored in my own contract, regardless of the kind of execution that Henry is running. So that is it with delegate call. With delegate call, one contract makes a call with another contract to make use of the function in the other contract. So you are only making use of the function. We are not storing the outcome or the output of that execution in the other contract. The output still comes back and is being stored in the contract that actually made the delegate call. So that is basically the idea of delegate call. So some upgradable contracts utilize delegate call. So just imagine that, okay, I know that Henry's contract now is implementing 1 plus 1. And by default, if a user interacts with me, I'm making a call to Henry's contract to run 1 plus 1. But let's say the developer at this point feels that, okay, I'm no more comfortable with running 1 plus 1. I want to run 1 times 2. So what I just need to do at this point is say, okay, I'm no more making a call to Henry's contract. I want to start making a call to Nemeka's contract. Nemeka's contract is implementing 1 times 2. So instead of making a delegate call to Henry's contract, I'll make a delegate call this time around to Nemeka's contract. And the output I'll be getting that will be stored on my own contract at this point to stop being 1 plus 1 that was in Henry's contract. And we'll start storing 1 times 2 that is in Nemeka's contract. So that is the idea of upgradability using delegate call. I don't know if that is clear. So guys, you understand?
Yeah, I understand.
Okay. So some of the way methods or some of the ways which we've been able to implement upgradable smart contracts are through eternal storage pattern. So with eternal storage pattern, the storage states, I think I mentioned this before, the storage states of the contract or the entire dApp is moved or is isolated from the function, the contract that holds the logic or the implementation. So instead of having one contract to run your dApp, you are going to be having like two contracts. One contract is going to be holding the states or the finality of executions, and the other contract is going to be holding the function logic. So your users are going to be interacting with the contract holding the state. So if a user wants to implement anything or wants to use any function in your contract, they make a call to the function, to the contract holding the state or like the storage contract. The storage contract is going to make a delegate call to the contract holding the function. Then the contract holding the function is going to execute the implementation. It's basically going to run all the computation, then send back the answer to or the results finality to the contract holding the storage and it will be saved here. So the idea is, okay, if you want to upgrade this contract, if you want to change certain implementations in this contract, all we need to do is change the contracts that you are calling, the contracts holding the functions. The previous one is still going to remain on chain. It's not going off chain. Once it's on chain, it's on chain. But this time around, we are deploying a new contract and we are going to now be making a call to this new contract that's holding the new implementation or the new function that doesn't have any bug or that has the updated features we want. So that is the idea behind eternal storage pattern. There's also the library driven pattern. The library driven pattern is an approach to upgradable smart contracts where the smart contract logic is divided into libraries. And the main contract references these libraries. When an upgrade is required, new version of libraries can be deployed and linked to the main contract. This approach allows for a more granular upgrade as you can replace individual libraries without affecting the entire contract. So at this point, I think I've mentioned the concept which might be new to you guys. It might not necessarily be new in like the real world, but in smart contracts, and you build it, you might be thinking what exactly are libraries. So libraries basically are like they're like smart contracts. They are contracts that contain logic implementation, but they do not contain state variables. Like they do not hold states. They have no storage. A library, like in the real life, a library just contain books, just contain their knowledge. You just go there, pick these books and read. That's how a library is in terms of like smart contracts. A library just contain code implementation, but it does not actually stores the execution of any of the implementation that is there. So we write when you as a programmer or a smart contract developer write a library for your contract, you're basically writing a smart contract that's holding functions, implementations, logic you want to use. You deploy this library. When you deploy this library, all you just need to do is make an external call to this library in order to run certain executions for you. For example, I'm writing a smart contract. I don't know if you guys know, but traditional smart contracts that we know and we write on like the security contract we write now, he has a size cap, he has a size limitation, which I think is around 24 KB or so. I might be mistaken, but around that range of 24 KB. So if you're writing a smart contract and you've written all your code, you've written your logic, and you notice that okay, at this point in time, my smart contract is exceeding the 24 KB size limit. So one of the ways we can go around this is you move some of the implementations to a library. Then you just know that okay, I'm reducing some of the bytecode or the code size of my smart contracts to these external libraries. And all I just need to do at this point is make a call from my contract to this library to run the execution. For example, I have a contract that this contract is supposed to calculate the CGP of a user. And after calculating the CGPA, we are going to run some execution depending on the person's grade. If the person is a first class student, we'll give the person 100 tokens. If the person is a second class student, second class upper, we give him 80 tokens or stuff like that. So, and my contract is already very big, very voluminous, and I want to reduce the bytecode of this contract. So, one way we can do this is you see the function that is actually calculating the CGP of the student. You can just copy as a function, put it in a new contract, like write a new contract for it, put that function in that contract, then deploy that contract. Once we deploy that contract, we know that okay, that particular function is collecting some arguments. These arguments are the student score for each exam. Then it's going to be returning the final CGP of that student. So my contract now, the main contract I have that is going to be issuing out tokens to this user, does not necessarily need to be able to calculate the student CGPA. All it does is that there's an argument that collects the student CGPA, the students scores for each exam. Then it's going to make an external call. It's going to make a call to that library I deployed. The library is going to run the entire execution, then send back the result to my own smart contract. So with that now, the library we deploy does not store the students. It has no idea of like okay, the final CGP of that student because it does not store it. All it does is okay, it collects an argument, runs computation, and give you a result. So that is one use of a library. So applying this now to upgradability in smart contracts, if I know okay to calculate the student CGP, I'm making a call to one library A that I deployed. Then after using it for like a month, I noticed that okay, there's a mistake in my calculations. I'm not calculating this student CGPA correctly. So all I need to do now is write a new contract, correct the mistake I made in library A, then deploy this library B. Then if I go to my contract, I'm going to change, probably there's going to be a function to change the address of the library I'm making a call to. So all I just need to do is change the address of that library to library B. And with that, If I'm making a call to calculate a student's CGPA now, I'm making a call to library B and not the previous library A. So with that, we've upgraded that particular smart contract. We've changed the logic, we've changed the implementations that that particular smart contract is running by. So that is what I mean by the library driven pattern. There's also the diamond standard, which is also known as ERC 4337. Is like one of the trending implementations for upgradable smart contracts. So to explain the diamond standard is a very, very large concept, and there are a whole lot of terminologies to it that I won't be able to actually cover or do justice to in just one sitting. So I'll just talk about it a little. Then I'll advise you to go and read about some of these things, especially the diamond standard. The diamond standard is a very, very interesting implementation. So the diamond standard is a more advanced approach that combines multiple contracts, each representing a facet of functionality. It allows adding and replacing facets while preserving the others. This design is used for complex multifunctional contracts with evolving features. So the idea of diamond standard is like, the way we have a diamond. With a diamond, each I think let me make it quick. Let me just Google something for 1 minute. I'd like you guys to see how the diamond facet is. Guys, can you see my screen? Can you see the page I'm on right now?
Yeah.
Okay. So
Interesting.
see, okay, I would like to advise that if at any point in time you guys have a question, just unmute yourself and ask. Because since I'm sharing my screen, I might not see the prompts that you have your hands up or stuff like that. So just do well to ask if you have any question. Just unmute yourself and ask. So you see the way this, for example, is a 3D illustration of a diamond. You know that's okay. We have, if you look at where my mouse pointer is, we have different patterns or different parts. We have this face, we have this face here, we have another face here, we have another face here. And if you keep turning the diamond, you're going to be seeing different faces. So this is one of the main like motivation or ideas behind naming the upgradability implementation of ERC 4337 as a diamond standard. So the overall idea is that the same way we have multiple faces for this diamond, we have multiple contracts, multiple smart contracts. And each of these smart contracts is intertwined together, they are tied together in order to implement a whole DApp. So multiple smart contracts are combined together and like joined together in order to build a functioning ecosystem or a functioning DApp. The same way a diamond has multiple phases, all coming together to form the diamond. With diamond standard, we have multiple contracts intertwined together in order to form a particular DApp. So the idea is for each contract you have, we are calling each contract in that diamond standard a facet. So each phase here is a facet. Each contract in your DApp is a facet. So the idea is there's going to be in the diamond standard, there's a mapping registering each function signature and the contract address holding that function. So the idea is each function has a mapping that is tracking the contract that actually holds that particular function logic. So if a user tries to interact with an ecosystem or a combination of contracts that's working as a diamond standard, if a user interacts with the entry point contract or the face of the contracts that users in that user interact with, that face of the contract and the user is passing in the function he wants to interact with. the this thing, the diamond faces, the face that's holding the entry point contract of the diamond standard is going to check this function this user is calling. Which particular smart contract address has this function? So once it finds the particular smart contract address that has that function, it's going to make a delegate call to that particular smart contract in order to run that function and store the logic in the face contract, the contract, the entry point contract that user interact with. So with this now, if you want to actually upgrade this contract, all we just need to do is we write a new contract that contains the implementation we want, deploy that contract, then add it to what we do is we cut it into there are terms that they use for diamond standard. So we cut it into the remaining part of the diamond. So just like we have different phases in this diamond, it's just like okay, we say we need a new contract now, we want to upgrade something. So we just implement or cut out a new phase in this diamond here. Once we cut out the new phase in this core diamond, we register all the functions in that particular contract in the entry point contract. So the entry point contract now knows that okay, there's a new contract here, and these are the functions now that are in that contract. So if a user is trying to interact with any of these contracts, I'm making a call to social contract address to know how to call any of these functions. So the idea behind, I think Diamond Standard is the most complex upgradable smart contract implementation we have, and it's also arguably as in one of the best we have so far. So it's a very, very interesting like concept. Right? You just need to go Google or research about ERC 4337. Okay. Okay. Oh my bad. I think I'm calling it wrong. ERC. Okay. Okay. So my bad. I meant ERC or ERC 2535. So I'm going to send these to the chats now. So it's going to be more like a personal research. It's a very important concept as a blockchain developer you need to actually understand. So research on that for your business outside the curriculum, but if you like to further your knowledge and that, just do research on that. So that is that for Diamond Standard. Then for the proxy contracts, I've basically explained how the proxy contracts work. And the example, the second section of this class is going to be basically focused on writing a proxy contract. So the proxy contract basically is able to achieve upgradability in smart contracts by implementing a multi-contract state where we have two contracts. So one of the contracts is called the proxy contract, and the second is called implementation contract. The proxy contract is going to serve as the entry point contract for users. And when users interact with the proxy contract, it's going to forward all function calls to the implementation contract. The implementation contract in this sense is going to be holding all the logic, basically the function logic, the function definition, the logic that each function is going to be carrying out. So the proxy contract forwards the call to the implementation contract. The implementation contract is going to run all the check, it's going to run all the execution it wants to execute, then send back the data to, send back the changing states to the proxy contract. So at the end of the day, all the changing states, all the record, all like the new state is going to be stored on the proxy contract. So that is basically the proxy pattern. You are going to be seeing more of that because you are going to be basically writing a proxy contract during the next section. So I'll just talk a bit more on it, then we'll go into the coding section very soon. So just like I said, for the proxy contract overview, we have a user here. The user is going to be interacting with the proxy contract. Then the proxy contract is now going to be making a delegate call to the implementation contract. The implementation contract in this case now holds all the function, all the logic we want to interact with. Then after running the computation, the change in state or the storage of the user is going to be stored in the proxy contract here. So that's basically the idea behind proxy contract. So some of the advantage of proxy contract implementation is that um, we have intermediaries for functionalities. So with proxy contracts, we are going to be having intermediaries behind between the user and the actual logic of the contract. So users don't necessarily need to know the contracts there, or yeah, user basically don't need to actually know or interact with the contract that holds the logic. All they need to know is okay, they interact with the contracts holding the state, holding the final outcome of all the whole computations. For example, if it is an ERC20 contract, which is like one of the most popular contracts we know, the proxy contract is going to be holding the balance of all the users. Then the implementation contract is going to be in charge of running things like the transfer for the bond, the mint, and stuff like that. So all the logic behind that is going to be in the implementation contract. So proxy contracts also help enhance upgradability. So by separating the contract functionality from its data, that way that if there's any issue in the data, it's not going to actually affect the storage. The final output, the storage, the user's balance, the storage is isolated from the functionalities, because you know that there might always be issues, there might always be problems with the functionality. But a user state, a user's balance, the finality of the user details are always going to remain the same. So with that, we'll be able to easily achieve upgradability, knowing that okay, we can play around with our function, play around with the contracts holding our functions, but we are maintaining our user storage, we are maintaining our database. It's just like in the web 2, we have the front end and the back end. The company now might decide to carry out an upgrade on their front end. They might basically change everything on their front end. You can go to this website and it's totally different, but the back end still remains the same. On the back end, they still have your data. On the back end, your balance is still there. Like everything about you, your details are still stored on the back end. All they just need to do is plug in this new front end to the back end, and the user basically continues using their platform or continues using their app. So that is like the idea behind upgradability and the proxy contract. So I've already explained what the proxy contract and what the logic contract is. I don't think there'll be any need to go further on that. I've also talked about delegate call and how most upgradable smart contracts use delegate call. So basically, just delegate call is like a kind of an implementation where a smart contract is delegating the call or a user's interaction to another contract. Contract A is making a call to contract B in order to use the logic in contract B. But the storage, the change in state, the final execution is being saved in contract A that is actually interacted with. So that's the basic idea of delegate call. So transparent upgrades. I think I've mentioned this during the course of the discussion that with transparent upgrades, users do not necessarily need to know that okay, there's been an upgrade in this smart contract implementation, because most users are more interested in okay, my balance. Okay, I still have my balance. I still have okay, I call this and I can withdraw my funds. I call this function, I can withdraw my funds, I can transfer to this user. They don't necessarily need to be bothered with okay, we've upgraded the contract, this and that. Stop interacting with this old address, start interacting with this new address. No. Our users do not necessarily need to be disturbed with this. They continue interacting with the old address or the old like contract address they have, but there've been a serious change in the logic that they're actually implementing or they're making use of. So that's one of the advantages of the proxy pattern. So the next thing we'll be touching on is the challenges and considerations. So while upgradable smart contracts offer significant benefits, they also propose challenges and issues. Some of these issues are ensuring compatibility between different contract versions is actually important. During the course of the demo session, I'll also be highlighting some problems that people might fall into while trying to implement proxy contracts. So imagine writing a smart contract. The first smart contract, like the main proxy and the logic contract that was written at first. Okay, it was written in 2018, for example, and we wrote that contract using Solidity version 0.7. Then in this 2023 now, a company wants to upgrade that contract. So okay, today now, let's say we are now using the most one of the popular version of Solidity now is about Solidity 0.8.3 or so. So imagine if you're using Solidity 0.8.3 now, and the previous contract was written in Solidity 0.7. You see that there's now different compatibility issues using the previous version of Solidity and a newer version of Solidity. There might be different executions, changes in the way Solidity actually work in these two contracts. So these might be some of the challenges we have, and it's most people they will advise you, okay, if you're writing a new smart contract and you're using the previous older version of Solidity, then my advice is to okay, just maintain the old version. In as much as you are the latest version now is Solidity 0.8.3, still go back and make use of the 0.7 that they are making use of when they wrote the first contract, because the storage that we are maintaining is written in Solidity 0.7. But sometimes the issue now or the bug might actually be in the Solidity version. Like, for example, the old version of Solidity is 0.6 and the rest, like below that, they didn't have any check to prevent overflow and underflow. And let's say you are now writing a new contract, and I want to upgrade your contract, and you need to write your contract in the newer version of Solidity that actually implements underflow and overflow. So you see that there's now some kind of disparity. Your storage contract does not prevent or does not protect against underflow and overflow, but the new logic contract you have is actually preventing underflow and overflow. So it might bring, in this case now, it might not be that much, it might not be, the disparity might not be too serious, it might not affect anything much. But in certain cases, there might actually be an issue, might actually be an issue of, there might be issues of incompatibility between the new logic or the new implementation you're writing and the storage contract or the old contract that you are maintaining. So that is one of the challenges, one of the issues with upgrading smart contracts using the proxy platform, compatibility issue. Then security risks is also another problem because malicious users can basically inject code, ingest malicious code into smart contracts. For example, very soon we'll be going into the bull run. We are going to be seeing a whole lot of shit coins that will be trending, pumping, put $100 today, tomorrow you're getting $1K and stuff like that. Some of these contracts, you might go to a task and okay, you say I'm a smart contract developer. Let me read and know if this contract is a shit coin. You might go through the contract and you're seeing like an implementation that is okay, like it's totally logical. But some of these contracts now they might actually implement a proxy pattern. And just one night like that, these guys will just upgrade the contract and remove the transfer function, upgrade the contract and disable transfer in some of these my ERC20 contracts. And just like that, the contract you were looking at yesterday, that okay, the transfer function is okay, nobody can remove it. Then you're coming there the next day and you're seeing a different implementation. You're seeing that one more. They don't change this contract code. Though. The contract code now is saying that nobody can actually transfer from this ERC20 contract. And you might be wondering that more some people will be saying I can't fat, say they can upgrade not contract and stuff like that. So some of these things are the challenges that we experience when it comes to making smart contracts upgradable. Then the next thing we'll be touching on before we end is the best practices. So when it comes to best practices for writing upgradable smart contract, it's always advisable to try to reduce the risk. One of the major reasons why people want to upgrade their smart contract is because there are vulnerabilities in the smart contract. So it's always best that you try as much as possible to reduce the risk associated with your contract. Try to write good contract, try to write good code. And aside writing good code, try as much as possible to audit your code before you push to mainnet, before they are pushed to mainnet. So it's always best to actually employ people that specialize in smart contract auditing. These guys are going to go through your code, try to find bugs. They can't actually guarantee that your code is going to be 100% safe, but to a great extent, you're going to be able to pinpoint some of the vulnerabilities that are actually in your code. So it's good to write comprehensive testing, like basically test your code very well, audit your code in order to maintain the integrity of your smart contract. So with this now, you actually be reducing the need for upgrades. And even when you upgrade your contract, you're actually going to be reducing the need for more upgrades on top of the upgrade you're making. So that's basically some of the best practices. So write good contracts, try as much as possible to go through your proofread your contract, reduce the bugs or vulnerabilities that might be in your contract. In as much as you can't actually write contracts that are 100% secure, also back it up by auditing. Test your contracts very well, audit your contract. So with this, you are going to be able to reduce the need, or yeah, basically going to reduce the need for upgrading our contract. So when it comes to reward application of upgradable smart contract, we've seen applications of upgradability in smart contracts in different protocols. We've seen DeFi protocols utilizing upgradability, proxy contracts, diamond standards, and stuff like that. So they can be applied in DeFi space. It can also be applied in decentralized governance, DAOs, and gaming, and also identity management platform. So with all this, we basically touch of I've called or most of the basic or most popular aspect of blockchain. So what this clearly means is that upgradability, proxy contract implementation, diamond standards implementation can basically be applied in almost every field of blockchain development. So whichever field you choose to specify in, there's always going to be an application, or there's going to be the need for applying upgradability in each of these fields. So that upgradability or upgradable smart contracts can be applied in basically every field of blockchain development. So with this, we've come to the end of this section one of today's class, which is just talking about upgradability, the different types of upgradable smart contracts, the need for upgradable smart contracts, and best practices and considerations for upgradable smart contracts. So I'll stop here to ask any questions so far, especially for some of us that are just joining the call. Do you guys have any question? Yeah, you can go on. Children.
Okay, there's this rule called a smart contract auditor. I just want to know if they also do safeguard smart contracts. If their duty is also to safeguard smart contracts from malicious attack.
Oh, okay. So no, when it comes to smart contract auditing, I think probably are trying to relate them or liken them to cybersecurity experts or stuff like that. Like the way you have some Web2 companies employ cybersecurity experts to protect their system or prevent some kind of hacks when hack, or like reduce the effect of hacks when they are going on in their system. But with auditing, it's not the same. Auditors are basically people that you employ or you pay to go through your code before they're actually being pushed to mainnet. So when it comes to block, you need to understand that when it comes to blockchain, smart contracts, and the rest, once you've written any implementation, once you've written your logic and pushed to mainnet, basically nobody can save you. If there's a hack now, nobody can save you. Most times, even before you notice that there's actually a hack, it's already too late. The what's going to even make you know that there's a hack is when you've lost funds or your money is missing from your contract and stuff like that. That's when you know that there's a hack. Or if you notice beforehand, okay, there's a hack, half of my money is gone. The only thing you can do is like to withdraw the rest. But I don't think there's anybody you can employ to say, okay, take your role is just basically to safeguard my contracts from being hacked. No, it's not. Once you've written your logic, you've written your logic. If there's a bug that can be exploited, it's going to be exploited. So the role of auditors at this point is just to proofread your code. Just like, okay, you're writing a book. After writing the book, you send it to I've forgotten what they call these guys that are going to actually read your book, correct any mistake, correct any errors or English or vocabulary errors or stuff like that. So that's how it is for smart contract auditors. Basically go through your code. If there's any vulnerability or anything, they point out these vulnerabilities and that's it. So the role of smart contract auditors is limited to just going through your code before you actually push to mainnet. So I don't know if that I think that should answer your question.
Yeah.
Okay. Okay. So guys, any other question? Sure. One quick and go on.
Good evening, sir.
Yeah.
I want to ask, but if a
Yeah.
particular smart contract now is exploited, and now like the protocol, like the platform now like okay, they're not looking for a solution. Since now they've been able to push everything to the mainnet. Which part of like how can the auditors like solve the problem since like they are trying to I don't know I'm trying to understand that part.
Okay, okay. So no. Like the work of the auditor comes in, or when the auditor comes in, is before you actually push to mainnet. So, just like here, let me use a good example. Like in school, during your final year, everybody has to kind of like do a project. You're going to actually write your project, bind your project, and stuff like that. And each of us is going to be issued a supervisor. So when you write your project, you write chapter one and two, chapter three and four, or you basically, if you want to, depending on how your supervisor is, you write the entire project. Say, for example, I'm going to give your supervisor. The supervisor is basically going to go through the project, tell you that okay, this is wrong, this is not right. There are issues here. Add this to this place. It's going to look better this way. Do this, do that, do stuff like this. Then your job at that point now is to take that project work back, run the edition or the corrections that your supervisor actually advised you to do. Then once you are done, or once the supervisor has approved that project, then you can go and present or submit it for final submission. So you submitting your project for final submission or you meeting your supervisor, it does not guarantee that you are going to correct all the mistakes. Because even after meeting your supervisor, running the corrections, your supervisor cannot basically see all the errors in your project. So after submission, there must also be an error that during your defense, external supervisor might point out and tell you that okay, this is not supposed to be like. And at that point, your supervisor can't do anything about it. So just it's connected or it's the same way as your auditors. You write a smart contract, you present that smart contract to auditors, external bodies to actually read. So you've not deployed at this point, you just write it, you zip the folder or anywhere you want to present it, send it to these auditors. Their work now is to read your code line by line, run it through some other static analysis software that they use to debug and find bugs. So if they go through these contracts, they might see error here, see error there, see bug here, see bugs here. Then they will write an audit report, a report, and send back to you that okay, we notice that there's vulnerability here and here. Correct this to this. Some of them might just say, okay, there's a vulnerability here, look for a way to correct this. So depends. Well, the major fact is that the work of an auditor is to go through your code, identify the vulnerabilities or the bugs in your code, then make this report to you before you actually push to mainnet. So if you go through these audit reports, you make the corrections, then push to mainnet. At that point, your work with the auditor is done. Your work with the auditor is basically done. So if you push to mainnet and they see vulnerability and your contract is hacked, the auditor can actually help you at this point in time. So it's either you just have to salvage the remaining funds that are left in the contract, then write a new one, or maybe there's basically even nothing left in the contract. I just have to go and start afresh. So that is that for auditors. The work of the auditor comes in before you actually deploy your contracts to mainnet. So does that answer your question, Harrison?
Yeah, yes, sir.
Okay. So any other question? Okay. So I'll probably take that as a no. So Guys, I think the next thing to do now is to try and set up our project. So we'll be setting up our Foundry project, then we'll try and write a proxy contract. We'll interact with the proxy contracts, then see how things go from there. So hope you guys will be coding along. So now before I continue, how many of you here have installed for Foundry? You have Foundry active on your systems. If you've done that, or if you have Foundry running your system, probably from the last class, I'd like to see your hands up. So I know how to go further with this class. If you have Foundry installed in your system, like how do you, when we were in the previous class, how do you guys follow along with the previous class if you don't have Foundry installed? Wow, that's serious.
I was there, but I wasn't coding along. I was mostly reading with the documentation as well as coding.
Okay. So we are trying to say nobody here has Foundry installed. That's serious. Okay. So I'm going to what we'll do now is I'll start try setting up a Foundry project. So I'll be expecting that you just try and follow up as much as you can. I won't be going back to explain much about Foundry because that is going to take or eat into the time for today's class. But I'll just try to take things slow so you can pick up one or two things. In short, it's not even possible because if I use Foundry at this point, some of you will be able to code along. So what happens is I'll just in short for today's class I'll use Remix. So we're writing our contracts, deploying our contract using Remix today. So in that case, all of you can basically code along using Remix. That won't be an issue. No excuses. So let's just go here. Then what we'll do, we'll create a new contract. So we are creating a contract. Let's start with let's start with first free. So can you see my screen? Is it too small? Right.
Yeah, we can see. We can see.
Okay. So what we're doing now is we're creating a new file. We are going to record this so create a file called Upgradeable contracts, a folder, sorry. Then create a file. We are going to be calling this file first free. Okay. So the idea now is I want to write a contract, a proxy contract. We are going to start with, as a company, we are creating a contract that user can increase their balance. Every user of our contract is going to have a balance with us. It's not going to be a complex contract. It's just going to be a simple counter contract. But the thing is, you align every user to set their balance. So if you set your balance, for example, me now, I'm a user. I'm going to be using our contract and I'll be setting my balance to 100, like an idea. That 100, that setting our contract to 100 is like me funding my account. And initially, we are going to be funding an account with 100 or any amount you want to fund. By first free or using our first free contract, any amount you increase your account by, you're going to get that exact amount. If you increase your account by 100, you're going to be getting 100. So the idea is that, okay, after a period of time, our company is going to decide that we don't want to be increasing users' balance for free. We will have to upgrade our contracts to add an implementation that if you're increasing your balance, we'll be taking 10% from you. So we are going to write a contract where each of you will probably interact with this contract. You will try and increase your balance. You will be able to increase your balance from 0 to 100 or 1,000, and you're going to get there. That's 1,000. Increase your balance by. Then we are going to upgrade our contract. Then add the implementation that users now will no longer be increasing their balance for free. For every increase you increase your balance, you are going to be sending 10% to our admin. So that is just the basic idea. So you are going to be seeing these contracts upgrade from or move from being free to actually charging 10% for each user interaction. So that is the idea I have on ground for today's policy contract implementation. So with that, we'll just be moving straight up to the actual coding. So we'll be doing our license identifier. I think it's just easier to just go copy this from here and Control C. So we don't waste time. Really back. So copy this, paste. We have our license identifier and start to the easy version. And the next thing we'll be doing is we'll define our contract. We're going to call this contract free contract. Okay. So with free contracts, in 256 for our state variable, we are going to be needing a 256 be a private variable. The we need this, we need this, we need this. Okay, let's start with an address. This is going to be our admin's address. And let's have a mapping. I know by this time you guys already know what the mapping is. We are going to be using this mapping to track the balance of users. So this is going to be in 256. We leave it as a public mapping. That way we're going to get have a getter function automatically. We don't need to write a getter function, a function to check users balance. So, users balance. And I think that's basically all. It's going to be a very simple contract just to study users balance. Then let's have a constructor. This constructor is not going to be taking anything, but it's also going to be storing our admin, instantiating our admin. So our admin is going to be msg.sender. So anybody that deploys this contract automatically is our admin. Then we're going to our function. Function set balance is going to take a unit type of a value or an amount that we want. It's going to be a public function. Then once you get the value, what we just basically need to do is we are going to say users balance msg.sender equal to, sorry, this one, anybody raise this hand? Okay, so we're going to be doing users balance msg.send plus equal to value. So what plus equal to does, I'm sure you guys already know by now. It's going to initially fetch the users balance, then add the value to it. So plus equal to is like get the previous one, add this to it. I think it's something you guys should know by now. Then this is basically going to set the balance of the user. Then the next thing we want is a function. It's not necessary, but just to be your admin, to be sure admin is rule, admin is supposed to be, it's going to be a view function, it's going to return an address. So what we just need to be here is, let's say, return admin, and we are good to go. So so with this, we basically have a free contract here. So I'm very sorry, at the moment my remix is kind of like clouded up. So what we'll do is, I hope you guys know on remix or even on your VS Code, you can write multiple contracts in one file. Yep, you can actually do that. So you can have multiple contracts in one file. So for today, let's try and add multiple contracts to this contract file. Since you are using remix, then we'll see how it's going to go. So the next thing, we're going to be writing our new contract, and this is going to be our proxy contract. And let's not call it, it's a proxy contract actually, but let's call it free token. We call it free tokens because since you align users to just come and increase their balance, they should get, you should call it a free token contract. So this contract free token, even though we are going to change our mind later in future. So yeah, one thing you guys should know is that when it comes to proxy contract, your states, your storage packing actually matters. I don't know how far you guys have gone, or if you guys actually understand what I mean by storage packing. Yeah, storage packing. If in this contract, in this under free contracts, now we know the first storage variable we have here is address admin. That means in this contract storage now on the EVM, at slot 0, the admin's address is there. Then the next storage slot after admin is going to hold this hour mapping. So if you are going to be utilizing the proxy contract, you need to make sure that this free contract, our main contract implementation, is actually going to be matching the storage slots that we have in this free contract. Unless we are going to be having serious storage clashes. I'm also going to be, thank God we are using Remix. I'll give you brief before deploying to testnets. I'm going to try and play around with this thing. Then I would like you guys to actually see these storage clashes actually happen. Then you get to understand why I actually meant that by saying it's important to make sure that the storage slots we have is always matching between the two proxy contracts or the contract you are trying to implement upgradability on. So since we want them to actually remain the same, what we'll do here is we'll copy out our admin. The storage slot of free contract at index 0 is admin. The storage slot of free tokens contracts at storage 0 is also going to be admin. Then at slot 1, we also add our mapping here. It's going to be a mapping of address unit, just like we have in the previous one. It's going to be public. And you have a user balance. So with this, you know that okay, the two contracts have matching. They basically have matching contrast to storage slots. So we need to add something else here. So one thing we need to add here now is address implementation contracts. Let's make this public so we can just get a getter function for it. That's something.
You meant to write users balance in the second contract instead of user balance.
Okay, okay, okay. Thank you, thank you. So yeah, I've corrected that users balance. Then the third line is going to be our implementation contract. So I'm just writing an IMPL contract here. So next we'll have is our constructor. A constructor is going to collect an address for implementation contract. So it's going to be doing two things. First of all, we want to make sure admin is equal to msg.sender. Then our implementation contract is going to be equal to underscore IMPL contract. It's always advisable. See, I don't know if it's possible to do. I've not tried this before, but it's always advisable to require that anytime you are collecting an address from user, just like programming will tell you in general term that do not trust your users. So since you know that if you do not pass a valid address at this constructor point, is going to actually break this contract because the contract is going to be making a call to address zero to know how to run computations. So I want to make sure that you're actually passing in a legit, a valid contract. So you can always check that required as implementation contract is not equal to zero. I've not really tried running this in a constructor, but sure it's working. So okay, that's it. Then if it doesn't work, if it's not a zero, want to throw an error to users, tell them invalid address, invalid MPL address. So what this basically doing is okay, it's telling our EVM to make sure or require, like just basically make sure that the implementation contract that we are passing in is not address zero, it's not empty, it's not like the valid, it's not like the zero address we are connected to you. If it's any other address, then accept it. So that's basically what this line does. And once our code passes this line, it's going to go straight to initializing our admin and implementation contract. But if it turns out that the address we passed here is an address, it's address zero, then the contract deployment is going to revert, it's going to fail, and to throw this error, invalid implementation address. So that is the reason why we have that required line down here. So the next thing is we want to have a modifier. I'm sure you guys know what a modifier does. I think yeah, we talked about it in the last class. So we'll have an only owner modifier. The reason why we want to have this one only owner modifier is that we are going to add a function down here, down later on, to upgrade this contract. I want to make sure that only the owner will be able to actually upgrade this contract. So that's the reason why we need a modifier. So for this modifier, I'll just use a require statement. And we are requiring that msg.sender is equal to admin, else create simple error, not valid color, or not authorized color, whichever one you prefer to use. So with that, the next thing we do is we put our execution line. So this line basically is to tell the EVM that once you see this line, execute any other contracts that has execute the contracts that the only other modifier is being called. So that's what that line does. Okay. So we're going to the main function, which is the set balance. Set balance is going to be collecting the unit data type or value. It's going to be a public function What else? Then, since we know our contract is going to be a proxy contract, our contract is not going to contain, that is, this free tokens contract is not going to contain any implementation. Instead, once a user call this set balance and passing a value, it's going to make a delegate call to the contract you have here, which is the free contract. Then the result of the output will be saved in the free tokens contract. So to achieve this, what we need to do now is what we need to do is we simply say MPL contract, that's our implementation contract, dot delegate call. Delegate call is a low level call, so it comes directly automatically with Solidity. Once you're using it in your contract, you just need to say dot delegate call. It's something similar to msg.send get address Ds and stuff. It comes automatically with Solidity. So all of you have access to it without any extra effort. So you just need to do delegate call ABI.encode. Oh no, let's encode this. ABI.encode. Okay, let's go with ABI.encode your signature. Then the way ABI encode works is ABI encode is going to generate a function signature for you. So what this is doing is we are calling delegate call on implementation contract. Then ABI.encode with signature is telling the EVM the function is going to call, and we're also going to be passing the argument we want to pass in. So ABI.encode with signature collects two arguments. It basically collects the function selector and the argument. So for this line, the function signature we are calling is, or the function we are calling is set balance. And set balance is basically the data type. So is this here? We don't need the value, we just need is the name of the function and the data type of the argument is collecting. Then we are going to be passing in the actual argument. So here we are going to replace arg with underscore value. Okay, so this should do it. Yeah, it should work. So once making a delegate call returns, we are not making use of the returns, the return value. Once you make a low level call, it returns two arguments to you. I think one is going to be the return value and also the success, like a boolean to track whether it's successful or not. So what we need majorly is the boolean to make sure that okay, this execution is successful. And since we do not need the other, we are basically going to leave it empty, just the way, just like destructuring in JavaScript. If you are destructuring a tuple, you just need to put comma and empty space, meaning that you do not need the other output. So once we've done that, we're going to require that our execution was successful. So we just require success. Else, so if it turns out that this execution is not successful, it's going to revert. It's going to like basically halt the execution, then return this error message you're passing. So once pass a message, function call failed. But if it turns out that this execution was successful, it's going to pass. Our execution is not going to be reverted. So with this, we've basically written that's one for our set balance. So if a user is coming to interact with this function, there's no logic here to actually add or increase the user's balance. But we are going to see that this user's balance is actually going to be increased and is going to be recorded in this mapping here. So I think the next thing we need to do is, okay, we already have a public mapping here. So let's just add the function. Okay, let's add a function to upgrade the contract. We're going to collect an address, and we're going to be calling the address new implementation, new NPL. It's going to be an external contract, external function, sorry. Then only our owner should be able to call this function. And the next thing we'll be doing is, just like I told you, anytime you're expressing an argument, whether it's from you or from anybody, require that, let's try to require that the address that is being passed in is actually a legitimate address. So the whether is not equal to, so you require that the address is not an invalid address. So okay. So after doing this, I think the next thing we need to do is to say we need to upgrade what do you call our implementation contract here? IMPL contract. IMPL contract is equal to underscore new IMPL contract, and with that we are good to go. So with this we've been able to implement two functions here. One is to set the balance of this contract. The second is to actually upgrade this contract. So okay, what do we do next? What happens is, let's write the third contract. You're going to have three contracts. One is a free contract. The second is our proxy contracts, which users interact with. Then the third is going to be the new contract you're going to upgrade to, that is going to be collecting 10% from users. So this time around, let's write a new contract. We're going to be calling this contract paid contract. So the previous was our free contract. What we have here now is our paid contract. For clarity, let's change this to proxy tokens. It gets be easier to understand. So we have our free contracts, we have our proxy contracts, which users will always be interacting with. Then we are going to be having the last part here, which is our paid contract. So for our paid contracts, just like I said, we need to make sure that we have matching storage slot. So we have our address admin and also our user balance tally at that point. Then the next we are going to have is our constructor that's going to initialize, which is actually not necessary, but let's just do it for. We're going to assign it to image.sender. Then the next function we'll be needing is set balance. Set balance, just like we said, it's going to be collecting value. It's also going to be a public function. Sorry. Going to be public. And so what we'll do now is you see users balance energy.sender, whoever is calling this, plus equal to we need to run some calculations here. So for the calculations, we need to say 90%. So okay, for 90%, you can see the value the user passed in multiplied by 90, then divided by 100. So I'll need to arrange this properly. Yeah. So what this basically does is, okay, the user is passing in value here, but instead of increasing the user's balance by exactly the value like we did up here, no, you say want to charge, you want to only increase user's balance by 90%. So 90% is also 90% of x is also x times 90 divided by 100. So that's basically what we did here. Calculate 90% of what the user actually wants. Then the next one we'll be doing is we'll now be saying user balance. This time around for our admin is going to be plus equal to underscore value subtracted by anything we have here. Mhm. So just for clarity's sake, what is happening here is, remember that, for example, if a user passing 100 here and we increase the balance of the user by 90% of 100, which is 90, then what we are saying here is that, okay, increase our admin balance by value, which is 100, minus 90%, which is 90. That means what we have here at this point is 10%. We could also choose to just say, let's just say, okay, but this is just to make sure that there is no wrong calculation on what we're increasing the user's balance by, the admin's balance by is the remainder of whatever we have left. But we can also always say 10 here. So this is going to be, you're increasing the admin's balance by 10% of value. Since you're adding 90% here, you're adding 10% to admin. It's going to make the entirety of what the user passed in here. Well, that's basically the idea we have. We are going to upgrade this contract, then see that our user's balance is not going to be increasing by 100% as we had before, but instead by 90%. So just for time's sake, let's make this public. Now it is on automatically get a function for it. So with this, you're basically good to go. Yep, we're good to go. We have everything running properly. So guys, who is following? Like, are you guys up to date on where I am, or do I need to give you guys time to catch up before we start deploying and interacting with this?
I'm following,
It's are
sir.
following. Okay, who else is following? Okay, something. Okay,
Sir, I have a question.
sure. Go on, ask your
Hello?
question.
Okay. That last line of the code, I want to know what is the function when you're saying about users balance.
This.
Yes,
Okay.
like
So
divided by
okay. So what I'm doing here is, remember I told you that this first function, the free contracts implementation, is increasing the user's balance by the exact amount the user is transferring, the exact amount the user is increasing. Like that's 100%. But in our paid contracts, we want that, okay, we want to be collecting transaction fee, for example. And the transaction fee is going to be 10% of whichever amount you want to increase by you want to increase your balance with. So what we did here is we basically said a user amount user is passing, multiply by 10 divided by 100. In Solidity, there's no way to calculate percentage directly. It's not like JavaScript that you can basically just say, okay, 10% of this. Or if you're pressing your calculator, you just say value times 10% or 10% of value, that kind of stuff. So with Solidity, it's not easy like that. So the only way you can do that is by using complex lines, okay, lines that look complex like this. Well, it's actually very simplified. Like, let's play around with this using 100. 100 is very easy to implement. Okay, if you go to your calculator now and you say 100 times 10 is going to give you 1000. Then 1000 divided by 100 is going to give you 10. So you see that at this point in time, 10% of 100 is actually 10. So with this, you've been able to calculate 10% of 100. Then for line 59, which is the line above us, above this one, that's this one here, we are taking 90%. So if you are using the same 100 to play with this, we say 100 times 90 is going to give us 9,000. Then that 9,000 divided by 100 is going to give us 90. And we know that 90% of 100 is 90. So that's basically what that line is doing. The line there is just taking, okay, what we're doing is we're increasing the user balance by 90%, then we're increasing our admin's balance by 10%. The 10% is more like a transaction fee that we've collected from the user. So that's what these two lines is doing. I don't know if that makes sense now, Chidman.
Yes, yes.
Okay. So guys, any other question before we go ahead with our interactions?
Yes, sir. Okay, I'm trying to. I don't know if I'm rushing. I'm trying to compile. Mine is showing error. Let me just.
Where is it showing the error?
Okay, the last contract, the paid contract. I don't know.
Which
Maybe
line?
I missed
Which exact line or what
line
point is it?
50. Line
What's
line
what's
50.
what's on your line 50?
I wrote contract, then paid contract with the curly brackets. I
Okay.
don't know. The thing is showing.
I think you should try and make sure that you're actually writing the contract outside the scope of the previous contract. So look around. Maybe you didn't close the curly braces like this curly braces now for the proxy contract. And
Okay,
if you're
okay, okay, okay,
mistakenly,
okay, okay.
I think that should be the problem, Jane.
Okay, yeah, it's fixed. Thank you, sir.
Okay. So any other question? Any other body? Anybody having any other issues? Okay. So ahead. Okay. So before we deploy to testnets, I would like to just play around with this on remix because I want to show you guys why it's important to actually have matching contrast data. So let's start with we'll start with our free contract. Let's deploy our free contract. So yes, we have our free contract deployed. This it. We'll copy the address. Then we'll go straight to deploying our proxy token. Our proxy token, remember the constructor at this point here is requesting that we put the address of the implementation contract. That is the address of the contract wants to making delegate call to. So we pass this and we transact. With this, we've deployed our proxy contract, and that's what we have here. So let's see. Let's set balance. No, let's first of all check balance. You can see the balance of this user, the admin, is 0. No. Yeah. You can see that the balance of this admin is 0. So let's increase this admin's balance by 100. Transact. Terminal execution field. Function call field. Okay. So this didn't work, and the reason it didn't work is reverted at this point, meaning that there's an issue with our delegate call here. Give me 1 minute to look at this. implementation contracts dot delegate call your API dot encode your signature function we are calling. Okay, at this point I believe this should work. So we need to let's look at the set balance also. Function public set balance plus. Okay. So let's try deploying the proxy to contracts. Let's copy this address. Proxy contracts. Then set balance 200. Okay, so this worked. So if you try to check the balance of the admin, so I think the problem then was we didn't specify the unit 256. Just use units. Yeah, you can see the user's balance is 100. So the reason why that previous one failed was simply because we didn't add the 256 here, and that was why it failed. So if you are following along and you use just units, I think you should also correct that and add the 256 to it. But with this, remember that our set balance function has no implementation here to actually increase this user's balance in our contract. It's basically just making a call to this free contract. And this free contract that has the logic to increase the balance and is increasing the balance. And we're able to, for example, let's increase user's balance again 200. If you come here and check, the user's balance is 200. And let's look at our user's balance. Our user's balance, this is it here. You are basically checking this user's balance in proxy contract, even though proxy contract does not actually have the implementation to actually increase or modify that mapping. So that's the main idea of delegate call and upgradable smart contract. But let's play around with this. Let me show you the reason why you need to. It's okay. So look at this now. Let's mix this up. On our project contracts, our user's balance is now taking the storage slot 0. And on our admin balance, on this part, the admin is actually user 0. Then the user balance is slot 1. But here we've interchanged it. Admin is now slot 1 and user balance is slot 0. So let's delete the proxy contracts that we deployed. Then try deploying another proxy contract. Okay, it's already here. Deploy. Yeah, Sunto, what's up? Sunto, can I ask a question?
Yeah, can you like tell me what you did to handle the previous error?
Okay, I just added 256. At the point when we API.encode with signature, I was just using units here, and that was why it didn't work. So I had to add 256 to it. So check yours. If you're also using units, change it to units 256. Exactly.
Sorry, I lost my internet. Please come again.
I said the problem is coming from, for me, the problem came from this line where I
Okay.
was using the API.encode with signature. Then set balance. I was using just unit here without the 256, and that's why I failed. So
Can I
you
see
needed
your
me to
implementation
specify
contract, please?
my which of the contracts.
The implementation contract, the first one, the free contract.
This is a free contract.
Okay, but the set balance here is just units.
It's just units. Yeah. By default, unit is actually if you put unit, it automatically defaults back to unit 256. So at this point here, in as much as I wrote unit here, it's defaulting to unit 256. But maybe when I'm encoding API.encoding, it's not picking up the 256 and it's actually requiring, or it's required that there are 256 is there.
Okay,
But
let me.
with Solidity, once you write unit, it automatically means that okay, you mean you need 256.
All right. Let me try now.
Okay. So while you're doing that, guys, I remember I swapped the storage slots of the proxy contract. So for slot one in proxy contract, we have the mapping that is tracking our user balance. Then sorry, for slot zero, I mean, we have the user balance mapping. Then for slot one, we have the admin. Then for our free contract, slot zero is the admin, then slot one is the user balance. So I want you guys to see what actually happens if you try to play around or if you have storage slots that are not actually matching with this. So what we did was basically to deploy a new proxy contract after switching the states or the storage slot. Then okay, nope, we need to make sorry, we need to make I need to make this public. It's important for this example. So let's deploy this again. So let's deploy our proxy contract again. So yep, we have our proxy contract. Then look at our admin. Our admin at this point is this address. Control C. Let's put it here. This is our admin. Then let's try to set balance 100. Press set balance. Our set balance was successful. And the person that called this function, 1 minute, the person that called this function is the admin. So we copy the admin's address. Let's check the user's balance. User's balance is still zero, meaning that this admin that called this set balance function, his balance didn't increase. But look at where the crazy thing now comes in. If you try checking, if you try checking the balance of this admin, okay, it's still remaining the same. So normally, once you try checking the balance of this admin, it's actually supposed to change. That's because there's going to be a clash here, and I'm going to be picking up a different admin or a different implementation here as the admin's address. Or someone has a hand, yeah, something.
Okay, yeah. I noticed that I'm not able to like increase the admin's balance using the implementation contracts. I can only do that with the proxy contract. Is that how it works?
You're not able to increase the user's balance using what?
The free contract, the first one, that implementation contract. But
Okay.
I can increase
Yeah.
it using the proxy tokens contract. So I'm asking, is that how it works?
So yeah, basically the idea is that users are not supposed to interact with the free contract.
Oh,
Users are not supposed to interact with the free contract. Users are only supposed to interact with the proxy contract. So the proxy contract will be the one to make a call to the free contract to run the logic or run the implementation that we want or that we have. So all your execution, all your interactions should be with the proxy contract.
yeah, I see. Thank you.
Okay. So, guys, we'll just set this back. Then, what we'll do now is, okay, let's deploy this. Then I'll like you guys to play around with this. Just increase your balance, see how it works. Then we are going to be upgrading it and using our paid contracts. Then you see that there's a change in the execution of the normal flow. But let's demo this with Remix first of all. So we've seen how the free contracts and the proxy contracts work already. So you know that from the proxy contracts, you can view the admin, you can set the balance, then you can come back and view the balance and you see that okay, it's increased to 100, normal is expected. Then let's change the user making the call to this second address. This second address is also coming to the proxy contract and increasing its balance this time around by 1000. So if you check the balance of this color, we're expecting to see 1000. 1000. But let's say at this point now, our CTO, the owner of this company, is no more comfortable with allowing users to perform transactions free of charge. So we want to start charging users 10% for their transaction. So all we need to do at this point is we come to this part. We deploy our paid contract. And that's it. We now have our paid contracts down here. We copy the address of our paid contract. Then we go to the upgrade function on proxy contracts, on proxy tokens. Then we're passing the address of our new paid contract and transact. Oh, sorry. Remember that we used the modifier here that only the admin that deployed it can do that. So we go back to our previous admin, then upgrade the contract. And yes, you can see it's now successful. So we're expecting our implementation contract to change to 652C. If you look on it, and here that's what we have here, 652C. So let's use a totally new user, the last user here. Then let's try increasing this user's balance by 1000 or so. So this user comes, he increases balance by 1000. So let's check his balance now. By default, using our old contract, we're expecting that the user is going to get 1000 also, but that is not going to be the case here. So if you call this, you see our user here now has 900 instead of the 1000 he's supposed to get. Then if you should check the balance of our admin is going to be having extra 100, 200 here. Admin initially staked 100, then got 200. But let's do this. Let's see. We are still connected to a different user. Remember the last user down here. And we checked our admin's balance. Now admin's balance is 200. Let's use this user to top up his balance too. The current user we are connected to, his balance is 900. Our admin's balance is 200. So let's just use that top up again. This user has topped up. Check his balance, he's getting 18, meaning that he got 800, the 100 went to our admin. If you should check our admin's balance now, our admin's balance should have increased from 200 to 300. And that is it. So you see that with this, we've changed the implementation of this contract from being free to now charging 10% of user's fee, or 10% of any amount users increasing his balance by. So what we'll do now is, okay, let's go to the deployment stage. We'll just deploy this contract and see how it goes. So we'll be deploying these contracts on Sepolia. So first of all, let's deploy our free contracts. Confirm. So we give it a while for the transaction to be completed on chain. So yeah, that's it. So copy the address of the free contract, then deploy the proxy contracts passing the address of the free contract and transact. So with this, we are deploying our proxy contract. The last thing we need to do now is to deploy our paid contract. Um, okay, so yep. Okay, so with this, you're running the last lab, which is to deploy the paid contract. So click OK. Our paid contract is coming up, and while that is coming up, okay, that's done. So what we need to do now is I would like to verify this contract so that wait, deploy the free. Okay, let's verify the free contract. For the free contract is the address of the free contract. Free contract is the address. Verify. Okay, that's good. Free contract is verified. So once I verified, I'll just send in the contract address here. So this is a contract address of the free contract. It's not compulsory for you to. You're not supposed to even interact with this contract. So our user basically do not need to even know about the proxy contracts, but I'm just sending it to you in case you want to go through the code base. Then the next contract we'll be trying to deploy now is the paid contract. So we just go here, get the address of the paid contracts, and verify. Okay, that's that. Then the last one we verify now is the proxy tokens contracts. Come here, proxy token contracts. Address of the proxy token contracts. Then that's verified. So what we'll do now is to go to Sepolia Etherscan. Just needs to confirm that the contract is actually verified. Okay, it's now verified. So this is the contract address of the first one. So let's go back and try verifying this again. So I'm trying to deploy or verify the proxy contract. the contract. Then implementation materials. Let's see if that's actually the problem. Okay, it said verification successful. Let's go back to the scan and try confirm. Still not verified. Okay, what's the contract address? That's an issue. There's 1 minute. Let me try verifying this contract. So I'd like you guys to actually interact with this contract. So, 0.8.18. Okay, let's see. Let's hope this works. Let's hope this works. So, passing the contact address as a positive answer. Uh, okay, so I think this should be verified now. Yep, it's verified. So, guys, I want you guys to just try and interact with this for Metascan. You can try and set the balance. That's this contract I'm sending now. If you are following so far, I would like to see a thumbs up. Like, I basically like to see a thumbs up. Let me know those I'm expecting to interact with the contract. Okay, Sonto Chiku, who else? Chidubem, who else? Ikene Harrison, yeah. Just three people. Henry, four. I've not heard from Victor. I've not heard from Chineche.
Yeah, good evening, sir. I joined the class a bit late.
Okay, okay, no problem. The record will be available. Just try and go through the recording. But
Okay,
what
thank
you
you.
just do? Are you with your system?
Yeah, I'm with my system, but I started with my phone.
Okay. So I sent a contract address to the last contract address I sent 28E6. So what I want you to do is just go to Sepolia Etherscan, then interact with that contract. So what I'm expecting you to do is basically just go there and set the balance, set your balance to any number. 100, well, use a number that you can easily calculate the percentage. You can set it to something like 100, 200, 300, 400. So that way it will be
Okay.
easier for you to see the difference. So once you've done that, I want you to, um, after doing that, type on the group chat that I've done it. Basically for everybody. Once you interact with that contract, type on the chat that okay, I've done it. So once I have like three people, then we'll move on to upgrade the contract. So guys, please let's be snappy. I'd like us to round up at least in the within the next 10 minutes. Sepolia Etascan to be precise, not Goli. And you're using the address that starts with OX28E6. To be more precise, this link I just sent will take you directly to the contract. So just click on this link, connect your wallet to Etherscan, then increase your balance by set your balance to any number, increment of 100, 200, 300, as much as you want. So it's just one example. So you tend to see the difference in these contracts and the difference that you get when you upgrade to a new implementation. So guys, please, who is done? Who is done? No, it's something that's very simple. I'm surprised that nobody has posted that it's done yet. So Sumto, Henry, Chidubem, what's up? Okay, Sumto is done. Henry, Chidubem, are you guys on your system? Like, what's going on? I need like three people before I move on. Ekene, um, Ekene Chidubem, what's going on? Are you having any issues on your end? Network. Okay. Where are you at the moment? Have you been able to access the link or what's the problem? Done, hey, done, okay. So you just need one more. Victor, how is it going?
Okay, I'm on it. I'll be done soon.
Okay. So what is going on? I think we'll just increase the page contrast. Copy. No, okay. So what I'll do first of all is, as you guys can see, I'm going to copy my wallet address. Then under the proxy contracts, let me check my balance. is my user balance. So I'm not going to set my balance to any amount. You guys are going to see it on this call. I'm not setting my balance to any amount. But by default, I'm the admin of this contract. So once I upgrade this contract to start using the paid version, I'm expecting that if you guys go back to interact with the proxy contract for a second time, I'm going to be taking 10% of any amount you increment your balance by. So once we are done with that, we are going to come back and check my balance a second time. And I'll be expecting that my balance should have increased to a combination of 10% from what each and every one of you increase your balance by. So that's just the overall idea or the overall knowledge of okay what we worked on today. So the idea is that okay we should understand how we're able to move this contract from being a totally free contract to being a paid contract without changing the contract address. You see, basically go to Etherscan and you see the same contract. You go to Etherscan, you see the same implementation, but the contract, as in the implementation or the functionality of that contract, have basically changed. So at this point, I think we should have given should be enough time for Victor or for Chidipin. So what we just do now is I'll just go ahead and upgrade this contract. So now we'll copy the address of the paid contract. Yes. Then go to upgrade. This then call the upgrade contract. So let's give it a while for the transaction to be completed, and once it's done, okay, that's it, that's done. So guys, some to Henry, I would like you guys to go back and interact with the contract again, and if possible passing the same amount you passed in the first time, like increase your balance again by the same amount. So once you've done that, also type down. So we'll just go back and confirm that my balance as the admin has increased. Okay, previously done. Okay, that's good, Victor. So go back again and try it again this time around. Increase it by the same balance. So now I'm expecting that for each of you that interacted with that contract, I should collect 10% from what you increase your contract by. And you're going to only be able to increase your balance by 90% of the new amount. So guys, we'll be waiting. Let's try and make it snappy. You're almost out of time. Okay, Henry said it's done. Some to Victor, what's up? While you guys are also doing that, let's go and check. So you see if my balance have increased. So this is my address. Check. Yeah. Okay. So my balance have, you can see my balance increased by 10 at the increase. So if my balance increased by 10, it means Henry actually increases balance, try to increase the balance by 100. So I'm sure Henry's balance now should be 190 instead of 200. Then my balance is 10 because I've collected 10% from Henry. So, okay, something you could also say is done. So let's see. Okay, still maintaining 10. I do not know how. So either 1%. Something, what do you increase yours by? Henry, what do you increase yours by? So one of you increased by 100. The person that increased by 100.
I increased by 100.
Okay, that means it's yours that went through. That means Henry's one actually hasn't gone through for me. Oh, Henry, what do you increase yours by?
By 1,000.
1,000.
The thing is, like, has not gone through.
Maybe
Let me try again.
you can try again. Okay, 1 minute. You can try. You can mute your mic again. Okay. Thank you. Thank you. Victor, how far? Okay, done. So let's see. I'm just about to call and ask you. Okay, yeah. Something else has gotten in. Victor too got in. So I'm guessing something increased by 1,000. Victor probably also increased by 1,000 because my balance now is now 210. So basically, I feel you guys should actually get the point now. We'll be able to move this contract from being free to being paid. The admin that previously wasn't making anything from this contract is now able to get 10% from every user's interaction from the same contract. It's a good thing and also a bad thing. A good thing in the sense that the admin now might be more comfortable and yes, okay, my users are now paying for transactions and I'm making money from this. But on the user's part, it might not be that nice because the user can wake up one day and try to interact with this function, this balance and see that it's only getting 90%. And if this were to be kind of like fraudulent transaction in a platform, I can choose to just I write an implementation that will make sure that you guys can't withdraw from your balance again. Me being the admin will be the only one able to withdraw from this contract. So the whole fact that our contracts are upgradable is like a double-edged sword. It comes with an advantage and also a disadvantage. So we as developers we should be able to actually scrutinize any contract, any platform you're interacting with, understand if it's a proxy contract, if it's an upgradable contract, understand the lapses or the problems that might arise from interacting with some of these contracts, then decide if it's worth the risk or if it's worth we invest in or interacting with some of these platforms. So with that, I believe I should have at least cleared out what proxy contracts are, how to implement an upgradable contract, and I'm sure you guys by now understand the concept of delegate core, how delegate core works and stuff like this. So before we end the call here, then I want to thank you guys for attending today's class, for also contributing, for interacting with the contract. So before we go, do any of you have any question? Is there any question you'd like to ask? So, guys, any question? Harry, Somto, Victor,
Okay. I
any?
have a question.
Yeah,
Um,
you
I'm
can
trying
go.
to I'm trying to write. I'm trying to click on write, but it's not showing anything. Like my the write button is not highlighting.
On which of the contracts, actually?
Like the first one, the one that
The
is showing
first,
increased by 100.
is it the contracts that start with 0x28E?
Yes.
No, it's supposed to actually work. 0x28E is okay. You're not seeing the right. Oh, did you connect? There's supposed to be a button. Are you seeing this? Did you try connecting
Yes.
to the Web3? Did you do that?
No.
Okay, that's the
O-
problem. You need to connect to
Okay. Okay.
MetaMask first. So after doing that,
All right.
before you can interact with it. I think I saw some of those hands up. Yeah, something. I'm going to your question. Yeah, actually. So go on to your question, something.
Yeah, I want to understand the difference between when we call a contract function using its interfaces, and when we call the same contract function as a delegate function. What's the actual difference?
Okay, very good question actually. So if you call a function a contract using its interface, it means every execution, every change of state is going to be recorded on that particular contract. So if you get the interface of a function like the ABI, you wrap it around the function address or however you choose to do it, then you make a call to a particular contract using its interface or its ABI. If you do that, then the change in state is going to be recorded on that contract. So whichever implementation you use, if you do 1 plus 1, it's going to get 2, and it's going to store the 2 in that particular contract you made a call to. But if you do run that using delegate call, interact with the contract using delegate call, and you do the same 1 plus 1, it's not going to actually store the true, which is the result in that contract. Instead, it's going to more of like trigger back to the person that sent it or to the contract that initially called the delegate call. So you just like imagine if you say something like msg.sender, like there's an implementation that says, okay, store msg.sender. If you use an interface to call contract A at this point is going to store msg.sender as the user calling it, like the EOA or the smart contract calling it. That's if you use an interface. But if you are calling that same contract using a delegate call from another contract, it's not going to actually store or record msg.sender. It's still going to be empty. Then the msg.sender in this case is going to be stored in the new contract that is making a call to it via delegate call. It's kind of like complicated, but the simplified understanding is that if you are interacting with a contract via its interface or API, any change in state is going to be recorded on that contract. But if you're interacting with that that contract via delegate call, the change in state is going to be recorded in the contract that is calling that contract via delegate call. So yeah, you can go ahead.
Okay, one more question.
Sure.
You said something about slot 0 and slot 1.
Yeah.
Is it compulsory to like make sure that like the state variables are the same in both contracts?
Yeah. So it's advisable to make sure that this not necessarily the same, but if certain execution, for example, if you are setting MSG or the admin in slot 0, try and also put the same slot. Like try and also put admin in slot 0 of the control that is calling it your delegate call. Because the way the whole delegate call work is that it's basically picking slots. It's running the execution with that slot. So if you're calling contract A, I don't know if this has a whiteboard. Is there a whiteboard here? There's no whiteboard here. Okay, yep, there's a whiteboard. I'm coming. 1 minute. Let's see if I can set up this whiteboard. Okay. So can you see the whiteboard? Something.
Yes, sir. Yes, sir. Yes, sir.
Okay. So basically, okay, you guys should forgive my drawing. So let's say these are two contracts, and this is storage slots 1, storage slots 2, and in this contract, you also have storage slots 1, storage slots 2. Then there's a function here that is going to add 1 plus 1. Then it's going to store it in storage slot 1. And this storage slot 1, you name it results, for example. Then there's a function here that's going to make a delegate call to this contract. So what basically happened is when the user now interacts with this contract makes a delegate call to this contract, to contract A. So the user interacts with contract B. Contract B makes a delegate call to contract A. Contract A runs the execution of contract B passing the value that it wants, 1 plus 1. Then contract A is going to run the execution, 1 plus 1 is 2. And normally it's supposed to store the 2 in results, which is in slot 1, this slot here. Since you are making this call via delegate call, it's going to send back data to this contract that the result is 2. Store 2 in slot this. Store 2 in this slot. So contract B now is going to pick up the response. Contract B now basically doesn't even know what you use to store, what's the name of the variable of this. like what's the variable name that you used to store this slot. All you just know is that okay, you received a call or like a command that store two in this packet in this slot here. So what it's going to do is okay, it's going to make a delegate call to contact A. Contact A will send back a response that store two in this in this slot. Then B is going to store two in this slot here and move on, and that is it. So in the sense where you've mixed your storage slots, the response that was supposed to be stored here, you moved it down here. And what you have here now is a very sensitive information like your admin address. What's going to happen here is that this two now that you're getting as response from slot A is going to override your admin address. And instead of you to have your admin address in this slot, you're going to be having two. And if there are any check you have in your contact, like make sure the only admin can call this function. At that point, the admin of this contract now has lost access to this contract because the contract will always be going back to pick the admin as ad number two. And that is going to be a very big issue. So that's why it's advisable that if you're using a process implementation, make sure you have matching storage slots. So that way you don't have any storage clashes or stuff like that. So that's the reason why I mentioned that okay, you should make sure the both of them have matching storage slots. So does that clarify something?
Yes, but I'm thinking again. Pardon me, sir.
Yeah.
I'm coming. I'm coming. Okay, yeah. This inside that proxy function, right? At the set balance. Sorry, inside this proxy contract, set balance function. In the structured view from the delegate call, right?
Yeah.
So is there not a way that we can also destructure maybe what the delegate call is returning also, and then set it to any way we want instead of using the
Oh,
slot
okay,
zero.
okay. No. No. This, to the best of my knowledge, it's not actually possible. I wish it was possible to hover on this and see the data that is being returned. But no, I think basically it's just you can actually destructure it and get like the outputs like that. What the way delegates call work is that you just make a call to this, gets the data slots, and the result should change, automatically changes it. So it's not as if you can get the data back and run some computation in it. If you want to actually do it by that way, then you won't be using a delegate call. What you'll be using there will be an external call. So an external call is going to make a call to this contract. You just make a probably then you make an external call to this contract, then you have to modify this contract. For example, if you modify this contract now, then tell it to return value. Basically, there's even no need with this. But if it were to be a more advanced computation, let's say you want to collect value, multiply it by 50 or stuff like that, you collect the value, multiply it by 50, then return the result here. If you return the result here, then what we do in these contracts, instead of using delegate call, is to make an external call. The external call will interact with this function, run the computation, then pick up the results we got here. Then when we pick up the results we got here, we'll now store it to the mapping of this particular user. Well, the goal is we don't want to run much computation or have much function logic in this our contract here. We just want it to make a delegate call, then store the logic without seeing any line of code here. So that's it with delegate call. With delegate call, you don't need to still touch on these things. It's like it comes automated. All it just returns to you is the boolean, whether the transaction was successful. Then I can't really remember what is supposed to be here. But that's basically it for delegate call.
All right, thank you.
Okay, no problem. Yes, I'm gonna try and see if I can find my ChatGPT. Yeah, okay. Let's ask ChatGPT. two arguments or two variables. One is the low level college day. Choose let's see if you can get a valid answer. Okay. So at this point, ChatGPT is not even functioning properly on my end. So I think what you just do is try and check it on your end, probably network issue. So check it on your end, see what it comes up with. But to the best of my knowledge, it's not possible to actually do that. Like get the outcome from a delegate call and still run some logic. Even if you're able to get the from the outcome and run some logic, it's going to be a duplicate transaction because by default, delegate call is always going to on the back end without you doing anything, stop the implementation. So if you choose to run extra computation by yourself, it's more like a duplicate. Well, that is that for your question. Okay. So any other questions, guys? Were you guys able to pick something from today's class? Do you guys fully understand Chidubem, Victor, Ekene, Henry? So you guys understand fully, or any other question before we end the class for today? Okay, Victor, that's good. Okay, one quite so good.
Um, so, sir, can you do me a favor?
Yeah, what is that?
Like, I would like to have the code, like the code for the class.
Okay, so what will happen is I'll create a GitHub gist, then I'll paste the code in that gist and send it to the WhatsApp group once you are done with this call.
Thank you very much.
Yeah, welcome. Okay. So in the absence of any further question or comments, so thank you guys for attending today's tech talk. See you guys some other time. Good luck. Good night. Okay.
Okay, thank you, sir. Good night to
You're
you too.
welcome. You're welcome.
Thank you,
Yeah,
sir.
thank you so much, Chinonso. Greatly appreciate. Right, guys.
You're
I guess
welcome,
that'll
guys.
be it for tonight. Yeah, as I stated yesterday, right, I'll be sharing like the stuff about the final project later on the group chat this evening. Good night, everyone.